Next part of the lecture will mainly deal with valving. We're going to come to that soon. Again, let us start with considering our capillary channel, where we have, for example, hydrophilic channel, where we have a liquid with a contact angle theta that is capillary filling the system. And we had derived the pressure drop of the system, which in this case is P gas minus P liquid, which equals 2 gamma over radius of the system times cosinus theta. Now we see that such a system either can be hydrophilic or hydrophobic. In this case, I have drawn a hydrophilic system, of course, because I can see my contact angle theta here is smaller than 90 degrees. And then I will find that this is a positive pressure, so I'll have a higher pressure in the liquid to the gas. Higher pressure in the gas and the liquid, but I'll see that I'll have that because the pressure here is the same as the entrance, that I'll have an actually positive flow in that way. If my contact angle theta is 90, so there's a liquid form that looks like this, and I see my cosinus theta becomes 0, and I see, of course, I got a flat surface, there's no pressure drop, and my liquid will stand still. There's no capillary effect anymore. This is typically what happens. So this is the case, for example, a glass tube. This is what happens if I have a silver tube, for example. Silver has a contact angle of 90 degrees with water, for example. And of course, I could coat my tube, for example, with Teflon, and then I would find that my contact angle, so here I have liquid and here I have a gas, then I see my contact angle here, theta would be typically 115 degrees. And now I see that actually my pressure here, the liquid pressure becomes higher than the gas pressure. So the pressure here becomes higher than here, but also higher than here. So I'll see that my liquid front will be expelled for my capillary tube. So because Teflon doesn't want to be wetted, it's hydrophobic, the liquid will be expelled, and because the Teflon likes to be dry rather than wet, so it will maximize its dry area and minimize its wet area. So I can say I can play with theta to get different effects. Now consider microfluidic systems will often be hydrophilic. Consider that I make an integrate microfluidic lab-on-a-chip system that consists of a number of capillary channels that are, I have 3 inlets and I have a reaction chamber, and I want to maybe synthesize or measure a product in my lab-on-a-chip. And then I enter a droplet at one of the inlet ports. What will happen is that because my system is hydrophilic, this droplet will be sucked into these microchannels and very fast fill the entire. So everywhere it will fill all the microchannels before I can even add a second droplet or a third droplet, and before I can control anything. So a capillary system by itself will just fill if it's hydrophilic, uncontrolled. What I need if I want to make a lab on a chip is that I want to have a spatial and a temporal control of my liquids. So I need to know which liquid is where at what moment of time. And therefore I will need to integrate valves. In Swedish that's a ventil. A valve is like a tap, like a water tap. If I open the tap, there's liquid flowing. If I close the tap, there's no liquid flowing. A valve does the same thing, but in a signal-controlled way. So that is what I'm going to talk about next: capillary valves. And here again, I see my general equation, and I see how can I now control the liquid flow. Well, there's actually 2 things I can do. My pressure drop here will depend on, the gamma I can't change, that is a material property, but I can control my contact angle, and I can control my radius, my geometry of my system. So this gives me 2 clues on how to make a capillary valves. Capillary valves dependent on the contact angle, and capillary valves dependent on the geometry of the system. And the first example we're going to look at is one where we look at the contact angle. So now consider a hydrophilic system capillary system where I have coated part of the section here with a hydrophobic material. Yeah, so it's not blocked the channel. I will now make a 3D plot so you understand what I mean. This is just on the surface. Actually, this is wrong. Let me take that away. So this surface is hydrophilic, sorry, and I'm just going to put a hydrophobic coating here. This coating will be hydrophobic. And in 3D, that would look something like I have a cylindrical channel, and in part of my channel, I have coated the inside of the channel with a hydrophobic material all the way around. So there's like a ring within this cylinder. Part of the cylindrical surface is coated with a hydrophobic material. And now what's going to be interesting is to see what happens if the system fills with liquid, with water, for example. So I added a droplet here, and of course what happens, it's hydrophilic, the first part, so I will get a hydrophilic system, and I will see that I have a capillary filling of my system. And my system will happily capillary fill until it reaches this position here. It reaches the hydrophobic patch, and then something will happen, or nothing will happen. So this is actually the first quiz question. And the first quiz question is, when this liquid reaches this point, will it be A, it will just keep on being in this shape. So this is the first one. It will have this shape. Or B, it will assume an absolutely flat shape. Poof. So that means something like this. Or C, it will actually try to enter, but then have to assume the negative, the more than 90-degree contact angle of this material. So this is the third case. So which of the three geometries, this, or this, will this droplet interface assume if I just let the system go? So the answer is that I can compare these three systems with each other. I mean, basically, I have a hydrophobic patch here, and here, and here. If I now consider the total surface energy of the systems, I see that for these cases, the wet surface, like this part, the liquid solid surface, is constant for all three. Yeah, it doesn't change for the three, it's just the same here. I see that the dry surface here, which is this area here, and this area here, I see that the dry surface, that's the solid gas surface, is constant for all three. The only difference I have is in the liquid gas, yeah? And now I can see which of the system has the minimal liquid gas. So if the only thing that the system does is actually minimize its total energy, and it can do that by minimizing its liquid gas interface. So of course the liquid gas interface here is minimal when it's totally flat. So the system will automatically assume a flat flow profile. So my liquid will fill, and it will assume a flat flow profile here. And when that happens, I have a cosinus theta c equals 90 degrees. So in that case, the pressure here will be the same as here, of course, a flat surface, no curvature, or infinite. Curvature is infinite. And so the system will stop. So my liquid will fill, and this will be a first natural state of the liquid. The liquid will fill until it reaches the hydrophobic patch and then just stop. So now I have controlled where my liquid, for example, this is one of three inlet channels of my chip. The liquid to go from the inlet channel and reach this position and then just stop. So I know where my liquid is. If I want my liquid to continue over here, I need to force it to go to this position. But of course it doesn't like to do, as said already, when it goes over hydrophobic, the liquid has a tendency to empty. But now I can calculate actually the pressure drop. The pressure drop generated to empty is actually given by this formula here. So if I want to force my liquid over this patch, I have to give an artificial pressure here. So this is a pneumatic pressure that I, as a user, will need to apply up front, or a suction here, is the same thing. Anyway, I need to apply a pressure drop here that is larger than this value here. So if I apply actively a pressure here, I can force my liquid to go over my capillary channel. And once I have a certain pressure, it will keep on flowing until it reaches, again, its hydrophilic part. And then here it will assume, again, the hydrophilic shape. And then I can let the system go. And after this part, it will continue filling capillarily. Because every further filling it does, it just wets more hydrophilic area, which it likes to do. So once I pass my hydrophobic patch, I apply a control pressure here. I force my liquid over the patch, and I can let go of the pressure. My system will keep on filling hydrophilically until it reaches the next valve.